Mainly, yeah, I will speak about, I mean, some top priority candidates, which could potentially help us to constrain all the physics we were discussing here, or at least this, feature. And then also I will a small introduction of what did we start to do with available method prescriptions and how efficient it is. So, okay, let's start from the beginning. Since ages, it has been assumed that one of the main features that could indicate the post-binary interaction is like high rotation of the former secondary star of a group. And kind of with this knowledge, we just look on the sample of like uniform sample of galactic O-type star and just took a fast rotating domain. By fast rotation, I mean with VC9 more than 200 km per second. Then we extensively started to really analyze each star in this domain. I mean, everything we could do, like proper motions, chemical compositions, by binary status, etc. We end up with this picture, but in order to like kind of understand it better, and also in order to kind of speak about these results with theoreticians, we need to divide VC9 by Vicrit. So then many people understand that half of this fast rotating tail actually rotating with like rotation in terms of Vicrit less than 0.5. Because then with this data, we can go to any of the simulations where people are kind of looking for OB plus neutron star or OB plus black hole, and like with this dashed area, which I show like it's all our targets should for example potentially have a neutron star as a companion. Okay. Then, if we will plot all of this target on the HR diagram, we can see, okay, they're kind of young, they're all close to the 0 H sequence. And also we can spot in terms of nitrogen abundances that around like 3 star. It's working or not. Okay. I mean, there are 3 stars which are really nitrogen enriched, and why they're so enriched. And in terms of helium, I don't see much enrichment, but if we will plot them like helium abundances as a function of VC9, that we see that, okay, yeah, we have some enrichment, small enrichment, plus if I will put here a kind of single track, like with, okay, with the initial rotation velocity of 300 or so 1 km per second, that even while star evolve, I can't reach this enrichment. But we should not forget about these things as error bars. They're kind of useful. But okay. Also, it's regarding fast rotating domain. But I would like to advertise tomorrow talk by Carlos, who will speak about slow rotating domain of all these type stars. So please also follow his talk tomorrow. Okay. Helium is okay, but if we will also put all the targets on the CMO diagram, there are also a lot kind of interesting thing is going on. We see that like on the right top corner, kind of very kind of enriched star, and also I put here kind of again single track evolution with a very slow initial rotation. And if I will increase the rotation, like it was 50 km per second, now it's 100, 200, 350 km per second, here I stop. So, and it's up to the end of the main sequence. Okay, I can't reach that bunch of candidates. And these 3 stars, particularly, it's this one that was that I show on the HR diagram. So they're nitrogen enriched, and they're really close to the 0 H sequence. So it's kind of very interesting actually to look on them. You can, I mean, I provide their names. Go for it. It will be interesting. And also error bars, because it's extremely difficult to measure all abundances for such star. And for the same target, we have kind of different thing, different measurements, but it's okay. It's important in which corner it's locating. And also, if I will put here another survey with magnetic slow rotator, fast rotator, but also galactic outward stars, we see that they're all spread around. But we have like one fast rotator with extreme high enrichment of the abundances. And from one side, to explain all the spread, we can go to the binary moves. And here, for example, is a track of donor of the Fiuki in terms of CNO. And if you look on the accretor, so it goes to enrich and doing the mass transfer at the end. Here is the Fiuki, like this process actual observed value, but with with a model, we can really reach this enrichment. So one of the explanation of all this, of that corner, it's of course binary interaction, but we really need to be careful that with a single star revolution, we can reach it as well, more or less. That's why we also need to see the actual age, like how rejuvenated it is. Okay, was about more or less single stars, and now we know that algos are extremely powerful projects, which they're really, I mean, it is really nice to study them because for that reason, well-constrained orbit, we know actual masses, inclination, and moreover, if we're able to disentangle VCNI of both components, it's also perfect because here is one of the systems we are studying nowadays, and here on the bottom panel is showing the actual VCNI for both. It's not VCNI, I'm sorry. It's already, I'm already subtract inclination, so it's already equatorial rotation velocity and also synchronization velocity on the current time. And as we can see, they are not synchronized, and especially in terms of primary, it's completely something interesting going on. And like we have another system, also not synchronized primary, and here we have a fast rotator, which is also far away from the synchronization velocity. So that's a thing. I mean, this, for example, I just showing this free system, which is kind of, I mean, they are top priority targets, potentially could help us to understand all this mass transfer and so yeah, it's just to show. And yeah, just to sum up, and then after all what we have different already available models which we can use, and then with a lot of which we already discussed caveats, which we really need to be careful, and especially the last point, which is completely under the questions. So, and just an example, I already showed yesterday, it's like another system. So we already start to fit, I mean, at least the location of secondary or primary and secondary. And I mean, since I'm working mostly in terms of rotation, these red lines are actual observed equatorial velocity, and it's extremely, I mean, hard to then spot at which precise moment we are see the system. So that's why it's kind of, we need to put a lot of effort in it. How many minutes I have? 2? I'd say 4. No, I think I even already can stop here because it's just a few other systems, but as you can see, even different prescription can show us different, how it's going in terms of mass transfer. And it's also main question, why different, with the same input, why is it different, have different tracks, which is kind of, we need to also sit and go one by one in this open lists, etc. So I will just leave with the conclusions, which are kind of interesting. So thank you very much.
Nice. Thanks for the nice talk. One quick technical thing just for us to discuss later, this Dujay accretion that you have as a free parameter, it might be a bit more unphysical of a choice to have that on and off. We can chat about that later. The other question I have is more or less to show this V over V crit that doesn't go all the way to critical. How much do you trust your V equatorial? My naive expectation as a theorist is that you get gravity darkening and you have a higher contribution from higher latitudes. So you're observing the slower rotating parts of the star naively.
True, it can happen, but we are not on that real critical regimes. I mean, in terms of critical.
Oh, you don't know. That's the thing. If you're critical, what would you see really?
Yeah, I mean, that's a good point.
Okay.
Thanks. I have two questions. First is that your galactic O-type stars, they can enrich surface nitrogen via 3 channels, I guess: wind, mixing, and mass transfer. So is there any way that you can break this degeneracy? And the second question is that some of your stars are from the mean survey. So you have these magnetic properties so you I wonder if you've looked into the correlation with the magnetic properties and the stars, and yeah.
Okay, yeah, I will first answer to the second, because I mean, I plot and I especially, I mean, distinguish like magnetic, not magnetic, fast, slow rotating, but they are kind of really spread around all of it, you know, so I think it's difficult really to understand, I mean, to distinguish it really where it comes from. And speaking about the first question, but first, yeah, I would like to for sure exclude the binary interaction and all this mass transfer and enrichment because of the mass transfer in this sample. So that's why I think it's first we need to make a simple star model, and then just to play as much as we can, kind of, can we reach such enrichment or not? But so without any binary interaction first, that naive approach, but then in terms of internal mixing and what is the 0 point of the abundances, things too. I mean, it's a big uncertainty.